Hello there, my name is Stefan Ceballos, and I am part of the HPC Core Operations Group at Oak Ridge National Laboratory, and I will be presenting Global Experiences with HPC Operational Data Measurement, Collection, and Analysis. Let's begin with what is HPC operational data and why do we care about it? HPC operational data covers the day-to-day operations data collected from the data center, compute systems, and supporting infrastructure and services. This can be separated into two categories, external and internal sources. This data is valuable to collect and analyze because it allows us not only to determine optimal operational parameters for this current generation of HPC systems, but can also offer some insight into future generations of machines as they continue to grow in computational power as well as in their need of facilities-related resources such as power, cooling, and space. A survey was developed to get a better understanding of why various sites in the HPC community are interested in collecting, merging, and analyzing data from the facility and HPC system domains. In addition to this initial objective, we are also interested in addressing potential issues of scalability, as well as data source interoperability. While there are sites that collect and analyze facility and HPC system domains independently, it is outside of the scope of this survey to understand the motivation and use cases for those sites. With these objectives of the qualitative survey in place, a global survey was designed with an initial seed group. This seed group included LLNL, LBNL, LANL, and NREL, which were all sites that the authors had contact with through the Energy Efficiency High Performance Computing Working Group. After the results from the initial design phase with the seed group, the survey was conducted during a one-year period in two steps. First, a brief cursory survey to identify focus groups, and an in-depth survey on the focus groups. Of the 20 sites that were reached out to with the cursory survey, 14 responded, and of the 14 that responded to the cursory survey, 8 supplied responses to the in-depth survey. With these responses, the team then began to synthesize results that cover technical aspects, use cases, and experiences. The architecture commonly used by the respondents of the survey is comprised of 4 layers. The first is the data source, where the collection takes place. The second is the message bus, the third is the database, and the fourth is the visualization and analytics layer. Using the survey results as a starting point, here's how you might begin to approach building an ODA system similar to the respondents of the survey. A great first place to start is identifying some target questions, followed by which data will you need to begin to answer those questions. From a technical perspective, look at how much data you're expecting to be collecting daily. Then determine your retention period for this data. With this information, you should be able to calculate how much throughput you will need for your message bus and your necessary storage capacity for your database. It's important to look at which tools you already have in your environment and come up with a plan on how you can add on to that, or possibly even how you can transition to your new stack. I recommend following sizing guides provided for whichever tools you plan on using and deploy these tools accordingly per the recommended guides. Once deployed, there will also be a phase where you will be tuning the tools for your particular environment. The scale of the platform will depend on the variety of the data collected, which may require a larger effort to maintain and develop these services. This type of architecture is frequently used in industry, so I highly recommend exploring what some well-known companies are doing with their data and how they've built out their platforms accordingly to make the best use of the data. One common theme you will find is that scalability is a key concept in the architecture of the tools themselves, which might lead to their overall popularity. Here is the technology matrix of the tools used at the various sites. A couple of interesting trends are that Grafana is used at sites that aren't using Elasticsearch, as well as at sites that are using Elasticsearch, in conjunction with Kibana, which is part of the ELK stack. MQTT is the choice for the message bus at the sites where Internet of Things is prevalent, and there has been an increased interest in Kafka, even though it is relatively new, especially when compared to some of the other tools in this area. Since the analytics components of ODA are still in the early stages at most sites, there are a variety of tools being used. Lastly, Splunk is used at a variety of sites, some more heavily than others, but it's listed in the other category due to its all-in-one data platform approach, where it covers the collection, database, visualization, and analytics altogether. However, this tool is used more frequently in the operations side of things. The use cases collected during our survey typically fell in one of these 6 categories. I'd like to go over some of these use cases with you today. The National Center for Atmospheric Research built one of the first supercomputing centers with a very low PUE. This was largely achieved because of the cold and semi-arid climate near Cheyenne, Wyoming, where NCAR is located, which makes it ideal for free cooling. NCAR's extensive sensors, monitoring, and building automation also contributed to their low PUE. They make use of the aggregated data from their site-wide electrical systems, facility mechanical systems, and HPC system cooling distribution units. This particular use case describes a power quality problem that was resolved using their extensive ODA capabilities. During small brownout conditions, they found that their HPC system would not go offline, but the variable frequency drive of the CDU pumps would fail and trigger a turnover between the 2 redundant pumps in the CDUs. This failure would occasionally cause overtemperature conditions in the HPC system's secondary cooling loop. Through integrated data analysis, they were able to correlate site-wide power quality issues with VFD failures. The NWSC staff then transitioned the CDU power from the direct utility to UPS-backed power. This enhancement gave the CDUs clean power, so they were no longer exposed to the brownout conditions as before. LRZ uses so-called energy-aware scheduling to lower the power consumption of their flagship systems. It is implemented in the job scheduler and leverages historical performance information from previous runs of an application to determine whether it is memory-bound or compute-bound. This is assessed based on performance counter statistics that are collected for all application runs. Under this regime, applications that are memory-bound may only run at a reduced CPU frequency. Since they spend many cycles waiting for slow memory accesses, they wouldn't benefit from higher clock rates and hence are not slowed down by the lowered frequency. The impact on the application's runtime is therefore negligible. Applications that are compute-bound, on the other hand, may run at the nominal CPU frequency since they can actually make good use of the maximum CPU performance. Although this may lead to a higher power draw of the CPU, this approach still reduces the energy to solution of the job as a higher frequency for such applications reduces the runtime accordingly. LRZ estimates the cost savings due to energy-aware scheduling at 1.8 million euros for the lifetime of their previous flagship system, SuperMUC. Riken relies on effective management of its power usage to keep in compliance with the contractual agreement between their site and the power company. They monitor the power usage of the facility as a whole together with the estimated power consumption of upcoming scheduled jobs on the supercomputer. For large-scale jobs, Riken requires users to first run a smaller version that allows them to obtain a power consumption profile through aggregation of application data and facility data. With this profile, they can then estimate the power consumption of the full-scale job and decide whether to schedule the job at a time when other consumption is low, lower the power drop from the grid by starting a backup gas power generator, or determine that it cannot be executed within the facility's current constraints. Riken's monitoring system can also detect if a running job approaches the upper limit of their allowed power consumption and will kill the job to avoid utility penalties. The Oak Ridge Leadership Computing Facility at ORNL leverages aggregated data to optimize chilled water temperature and flow for energy efficiency. For the Summit supercomputer, the OLCF currently uses medium temperature water in the secondary loop to minimize the use of chilled water. The use of medium temperature water enables the use of water side economizers based on evaporative cooling when the weather conditions are advantageous. To further reduce the use of chilled water, especially when the economizers are not efficient, the OLCF uses the aggregated data to optimize the cooling water temperatures and flow rates. Facility engineers are given access to a holistic view that has the mechanical and environmental data from the central energy plant, as well as the power and thermal data from all GPUs and CPUs. With this view, the delta temperature between supply and return is maintained high, but in a way that the GPU and CPU temperatures are kept just under the threshold of throttling to help O&L increase the amount of free cooling they can utilize, even on days with adverse wet bulb temperatures, and thus improve the site's energy efficiency and OPEX. To optimize the energy efficiency performance of facility cooling systems in an ongoing manner, NERSC uses multiple ODA systems, assembled in an operations monitoring and notification infrastructure system referred to as OMNI. Here are two project examples. Firstly, optimizing cooling water plant settings. Finding an optimal minimum cooling tower water supply temperature set point is often a slow process with complex engineering analysis and calculations. Figure 4 in the paper shows an example of an automated and real-time scatter plot feature of the Omni system. This visualization shows how NERSC can segregate before and after time periods in order to evaluate the overall cooling plant power draw performance due to system setting changes. This has proven to be a powerful tool in optimizing infrastructure system performance in an agile manner without project management overhead or slow implementation timing. The second example is better estimation of cooling supply air demand. Another optimization project underway at NERSC is to leverage the Omni system, which uses Prometheus clients installed on facility air-cooled IT equipment. The client reports the intake air temperature and fan speeds of the IT equipment, giving NERSC the ability to sum cooling air demand and therefore better inform cooling air handler supply settings. This strategy promises to be more agile for energy performance than simply setting the infrastructure supply air rates based on a cubic foot per minute per kilowatt rule of thumb using the IT equipment power ratings. These two system optimization examples are among many more enabled by NERSC ODA tools as part of an ongoing effort to keep facility operating at a 1.1 or less average PUE performance target. We found that there were some pull and push factors that drove our surveyed sites to develop ODA capabilities. The most often reason was because it went along with other objectives to improve energy efficiency of the HPC operations and cooling infrastructures. Interestingly, the sites that did not respond to the survey because they do not see the need for aggregation between data collected for their facility and HPC systems also are not bound by energy efficiency related constraints or mandates. Sites with power limits imposed by either utility or internal organization require detailed monitoring and analytics capabilities to ensure their HPC systems can safely operate. Some sites are also developing these capabilities out of interest in pushing science and gaining deeper insight to their systems and facility. Lastly, only a few sites have system administrators leading the efforts to aggregate the data collection of the facility and HPC systems, while most sites have facility engineers and/or researchers leading these efforts. Other interesting observations include many of the sites had a build it and they will come experience during the design and deployment of their ODA systems. Although they had certain use cases and users for the collected data in mind when they deployed it, they found further use cases as well as users once the data became available. Another common theme was that those that used NoSQL databases for their monitoring saw additional benefit in being able to scale those databases horizontally. This also allows for higher frequency data, more monitoring components, and longer data retention time. Sites mentioned in their survey responses that they were beginning to further develop the analytics components of their ODA systems. Incorporating machine learning and automatic control feedback loops into production appear to be what most sites have in mind for their next stages in ODA. Tightening integration with application performance data is also on the to-do list for some sites that are not yet doing so. For sites that plan on engaging in ODA, the key lessons are that there are tools readily available to build out telemetry collection, aggregation, and analytics pipelines. With advancement in this general area, these ODA solutions are technically feasible as scalability and storage space are no longer limiting factors. All sites have use cases where the availability of monitoring data was beneficial for operations and led to cost savings. Having this available data often leads to new use cases and potential users of the data that would not have been anticipated prior to the deployment of their ODA systems. For the ODA community that is already engaged and has ODA systems in place, the key findings are that the automated analysis processes are still being developed, but there is analysis currently being done manually. Sites also believe that there are additional use cases to be worked on that make use of both facility and HPC system data, but existing use cases in this space is still rare. Thank you.